Okay, thank you. Hello, everyone. Thanks for coming. Okay, so my name is Michał Jamroż. I'm one of the co-founder of deep learning startup Craftinity from Krakow. I'm also a PhD student at AJH University at Krakow. So today I'm gonna talk about image generation with deep learning techniques. And because the models which generate images are called generative models, the talk is gonna mainly be about deep generative models. So at the beginning, I will introduce deep generative models in general. Later, I will say something about two most popular nowadays classes of models, that is variational autoencoders and generative adversarial networks. And within each class of model, I will briefly say how can they be used for semi-supervised learning tasks. And at the end, I'm going to show a case study with some results. Okay, so as I said, the models which generate the data are called generative models. So what do we expect from the generative model? If we train the model on some data set in either unsupervised or supervised way, most often unsupervised, after that we'd like the model to generate the samples which closely resembles the samples from the training data set. So if we are working in the domain of handwritten digits, then we'd like to generate images which look like handwritten digits. We want neither random noise, we want neither cats nor letters. So this problem of data generation is not new, and it's often tackled by modeling a probability distribution over the data space. So for instance, if our data are images of 500 by 500 resolution, the whole data space is all possible assignments on 500 by 500 grid. So again, if we are working in the domain of handwritten digits, we'd like the model to assign a relatively high probability to samples which looks like handwritten digits and low probability elsewhere. So in the history, people came up with some examples like sigmoid belief networks, like deep Boltzmann machines or DBN. This last model especially has a merit of igniting the boom of deep learning, but nowadays it rather has a historical meaning. It's not widely used. So let me introduce more recent examples of models. So the first one is variational autoencoders class. Okay, so variational autoencoder is a latent variable model. What does it mean? A latent variable is a variable which is unobserved but influences the value of the data. So for instance, in probabilistic machine learning, latent variable models are very popular. For instance, mixture of Gaussian or probabilistic PCA is one of the examples. Later, we have a deterministic function f, which maps the latent variable to our data space. And this mapping f is used to define the generative distribution p of x given z. So the f is not encoding our image directly, but it's only used to define the probability distribution x given z. Okay, so because neural networks are a nice tool to model complicated mappings, we choose the f to be a neural network, and very often p comes from some parametric distributions family, so it can be a multivariate Gaussian, for instance. And the output of f is used to represent the parameters of this distribution p. So for instance, if our p is a Gaussian, then f encodes its means and covariance matrix. Often, because the dimensionality of x is often very large, in case of images, then we restrict the covariance matrix to be the diagonal matrix. But obviously, if our data is binary, then we can use Bernoulli distribution. Okay, so the process by which we obtain our data, our samples from data space X is simple. At first, we sample Z from some prior distribution P of Z. It's usually a Gaussian with zero mean and identity covariance matrix. Later, we pass this Z through the neural net. It encodes our parameters of the P, and later we sample the data from P. How many of you knows about denoising autoencoders models? How many of you know about the denoising autoencoder models? Okay, so right now it may be not clear why we call this, why this model has something to do with autoencoder. So it will, I hope it will become clear when I say something about learning the variational autoencoders. Because we have the neural net in our generative distribution P, then neural networks have a lot of parameters. So we need to feed these parameters to the data. So here we adopt the maximum likelihood learning procedure. So let's say our data set X comprises n samples, and our goal is to choose these parameters. Theta of these parameters, theta are the parameters of neural net, which maximizes the log of the probability of whole observed data set. This log of the probability is called a likelihood. So to visualize this, if our likelihood depends on the parameters in some way, then we look for these parameters, which maximizes the likelihood. Okay, the variational autoencoder model allows us to compute the P of X, P of our sample. So this is just a marginalization of the joint probability of X and Z. But the bad news here is that the Z appears under this integral in a very complicated way, because we pass the Z through the neural net. So because neural net is a series of nonlinear operations, then this integration is almost often intractable. So we need to choose some different procedure. And we train the VAE by introducing some function which has values always lower than our true likelihood, but is close enough to the true likelihood that when we maximize this lower bound for parameters theta, we also obtain a good solution for the true likelihood. Okay, so let's wrestle with math a little bit. Okay, to derive the lower bound, we introduce some distribution Q over Z, and later use the Jensen's inequality to lower bound our likelihood. So it holds true for every distribution Q. But the more interesting thing than the formula for lower bound is rather the additional term, which we need to add to the lower bound to get our likelihood, because it appears that this additional term is a distance between our distribution Q and posterior distribution of Z given X. So it appears that we are getting closer to the true likelihood with our lower bound when distribution Q is close to distribution to posterior P of Z given X. So here's the visualization of this phenomenon. Okay, and because we like to have the Q as close to the true P of Z given X as possible, we will formally introduce the conditionality of Z given X, and we can do the similar trick for Q like we did for P, for generative distribution. So now we can use the neural net to encode the parameters of Q. So now the neural net encodes from X observed data space to latent space. And okay, So because we had to derive the lower bound, we now have now two distributions involved with VAE. The first one is the generative P, and the second one is the posterior Q. Okay, so the P takes Z and gives us X, and Q takes X and gives us a Z. So now the analogy with the noising autoencoders may be clear, because the noising autoencoder is basically a neural net which has two pieces. The first one takes the input and through some series of operations gives so-called code, and later the second piece of the network takes the code and reconstructs our input. So the same we have with our variational autoencoder, but here we are working in the probabilistic framework. So instead of deterministic neural networks, we have neural networks are used to model the probability distributions. Okay, and the last argument that a variational autoencoder is actually an autoencoder is when we decompose our likelihood, which becomes our training objective, which we decompose into these two terms. So the first one is reconstruction term, and the second one is regularization term. The reconstruction term is called because the model, both encoder and decoder, has to do a good job in reconstructing the data, because for given X, when we compute the latent code Z, later the generative distributions has to assign a relatively high probability that X was generated from Z. So if you know the denoising autoencoder's training procedure, it's similar there, because actually the objective is just the minimization of reconstruction term. Okay. So here's the model. We have some original image X. We have the encoder, that is this Q distribution, which gives us the probability over the latent space. And later we have the generative distribution, which encodes our latent variable into our data again. Okay, so when it comes to semi-supervised learning, deep generative models, both variational autoencoders and generative adversarial networks, are a very promising approach to semi-supervised learning. So when it comes to semi-supervised learning with variational autoencoder, then here our data is a result of the generative mapping not only from the latent space Z, but also from labels. So here now the neural net takes input of both types. Okay, and similarly to training the VAE in unsupervised way, here we also optimize the lower bound for data point, and depending on whether the point has label or not, we are either bounding the joint distribution of X and the label, or if the point is unlabeled, we lower bound only the P of X. Okay, I have no time to derive these equations further, but please consult the paper. This semi-supervised learning with deep generative models written by Diedrich Kingma and Max Welling and some other authors. Actually, Diedrich Kingma and Max Welling are the authors of the original paper, Autoencoding Variational Bias, which introduced the variational autoencoder model and ignited the research of this class of models. Okay, so next class of models, generative adversarial networks. Although the variational autoencoders are quite a hot topic nowadays, there's a lot of research being done there, but GANs, I think, are the most popular deep learning models now, and they are heavily researched, the most heavily researched among among the deep learning models. So, okay, the GAN framework introduces two components. The first one is the generator, and the second one is discriminator. Similarly to the variational autoencoder, the generator also takes some latent variable z and later transforms it into the data space X. So when it comes to data generation, our generator is enough. We don't need discriminator to generate the data, but the discriminator is used to train the GAN models. So actually, the generative adversarial networks introduces a new way of training neural networks, introduces new objective, and I will describe what is it about. So okay, generator generates our data, and simultaneously the discriminator tries to classify whether the example is real or fake. We are training GANs on some data set, so next to the generated samples we also had the real examples coming from our data set, and discriminator tries to say whether the data which we put into it is real or fake. Okay, so formally we have our dataset X, and from the discriminator's perspective, we'd like the discriminator to assign high probability that the sample coming from our training set is real, and simultaneously we'd like him to assign low probability that samples that are generated by the generator are fake, are real. So when it comes to generator, on the other side, we want him to generate samples which are so realistic that they fool the discriminator. So on this generated samples, the discriminator will say that, okay, this sample is probably real, although it's fake in real. Okay, so when it comes to objective, the whole objective comprises two terms. The first one is responsible for the discriminator to assign high probabilities on the real data that they are real. Okay, and the second term introduces the conflict between generator and discriminator. Because from the discriminator perspective, we'd like him to assign low probability that samples generated by generator are real. But when it comes to generator, he tries to fool the discriminator. So he wants the discriminator to say that the samples which he generates are real. So actually, the training generative adversarial networks consists of solving so-called min-max game. And the training procedure here it's a complicated thing because the basic procedure consists of alternating between updating the discriminator parameters and updating the generator parameters. But honestly, every GAN network I used to train in the past was trained with some other procedure, with some modifications to this basic one, because the training of GANs suffers a lot of problems. Okay, so when it comes to semi-supervised learning with GAN, I'm going to describe the idea introduced in Improved Techniques for Training GANs papers. Among the authors, there is Ian Goodfellow, the author of the original papers for GANs. So, okay, so now the discriminator is used as a classifier for the data. So we extend its output from 0 and 1 to predict all k classes, plus we add the additional k plus 1 class, which is responsible for predicting that the sample which is fed to the discriminator is fake. So when it comes to, so now, probability that X is fake is the responsibility of the last output of the softmax of discriminator, and probability that X is real is just the sum over all softmax outputs from 1 to K. So when it comes to the objective, we decompose it into the supervised and unsupervised terms. The supervised is responsible that the discriminator classifies the data properly, while the unsupervised takes care that discriminator classifies the examples from the dataset as real, and the second term is that it's not fooled by the generator. So for samples generated by the generator, the discriminator has to predict the k+1 class. Okay, so maybe I will show some results. Okay, so the first one is image generator. I use the celebrity faces dataset to train both VAE and GAN in unsupervised way. The celebrity faces dataset is a big dataset comprising over 200,000 faces of famous people. And since there's the visualization of some of the examples, it's just the photo of the face. Okay, so when it comes to generation the faces by VAE. So to remind you, the process is simple. We sample the latent variable z, pass it through the neural net, and sample from the generative distribution Px of z. So, okay, so let's take a look at the samples generated by VAE. It's something like this. So actually it's undoubtedly a face, but the first effect we can see on these images, it's kind of blurriness of the images, and this blurriness is a peculiar feature of autoencoders, and actually it's not fully understood why it happens. But one of the possible solutions to mitigate this effect is to use some extension of the variational autoencoder. For instance, deep feature consistent autoencoder, which adds an additional term into the loss function, may be the solution. Okay, and our autoencoder is also able to reconstruct the data. So we pass the original image to the autoencoder, we encode it to some code, and later decode it with generative distribution P into the original data space. So let's take a look. What are the results of reconstruction? And actually, he's not doing well in reconstructing faces. In some examples, the feature of the face are saved, but there are a lot of quite spectacular fails. For instance, Elon Musk and this face. It's probably not the best reconstructor, but probably some parameters of the training should be adjusted to improve it. Okay, so when it comes to generation the images of GAN, so okay, it's the results of the VAE, and here is the examples by GAN. Okay, so shapes are definitely sharper than in case of VAE, but still there's some surrealistic effects added into these faces. So they are quite distinguishable from the real examples. Okay, that's the other example. And when it comes to semi-supervised learning, I perform an experiment on CIFAR dataset. That is, I split the training dataset on labeled and unlabeled dataset. So I did it with the split of 1K, 2K, 4K, 8K, and 50K of labeled images. And what's more, I trained the later I trained the fully supervised CNN with the same architecture as the GANs discriminator with the same split. And let's check what's the accuracy for CIFAR dataset on test dataset. So here are the results. So when we have very few labeled examples, actually the GAN trained in semi-supervised way outperforms a lot the supervised CNN. And as we are having more labeled examples, this gap is getting smaller. So in the end, if we use all of the labeled examples for CIFAR, the accuracy is almost the same. Okay, and here are the samples generated by GAN trained on CIFAR. It seems that as our labeled dataset is bigger, then the samples are probably the better quality. But anyway, again, when it comes to technicalities, for experiments, I use the TensorFlow, obviously Python, and the tensor layer library built on top of the TensorFlow. I also use the code which was published by authors of various papers. Okay, so that would be enough. Thanks for your attention. If you have any questions, then feel free to ask.
I told you it's not going to be very easy. Questions? First, one or two questions.
So are there any guidelines what kinds of architectures work best with GANs? I mean, you presented an architecture, but you I think deliberately left out the part whether you have CNN inside or put something else inside. And does it matter a lot?
Yeah. I didn't talk about architectures, but for the generator, I use the pretty popular architecture which involves a series of deconvolutions. And in order to improve the training, also the using batch normalization layer is a very needed thing. And when it comes to discriminator, on the other hand, I use just a similar architecture to CNNs, which classifies the data. So, for instance, there is a series of convolutions, max poolings, and so on. So when it comes to architecture, there is nothing special there.
And are there any I mean, you presented images as an example, but are these methods also used for speech synthesis or music synthesis or something like that?
Yeah, obviously these are generative models. Yeah, the models will generate the data. So, but obviously depending on the type of the data we are working, whether text or audio signal, we should obviously use the proper architecture for that. So, for instance, in NLP, variational autoencoders where we use the LSTM layer in either decoder or encoder, VAE is a very popular choice.
Okay, thank you, Michał, for your talk, and yeah, big applause.
Thank you.